surgical medic on your screen, and you'll be going into, you know, that aspect of physics that JAMB loves so much. Dimensional analysis. Yeah, dimensional analysis. Yeah, this is what we are looking at. Alright, so yeah, let's what do they mean by dimensional analysis before we jump into, you know, the calculation aspect? Should you call it calculation? Yeah, we would call it calculation actually. Alright, so dimensional analysis is actually showing the relation between, you know, your derived quantities, or let's say, you know, the relations of derived quantities from that of, you know, fundamental quantities from which they are obtained. You know, I told you what derived quantity is in our last class, that derived quantities are actually coming from our fundamental quantities. Are you with me? So fundamental quantities are those quantities that we use, you know, as our basic quantities. You get, we use them to obtain derived quantities. So simply, you know, these fundamental quantities would actually be represented using symbols. We can call them symbols, we can call them alphabets, but the combination of these alphabets, or the combination of these symbols, are the one that will now give rise to our derived quantities. Are you with me? So if, for example, if fundamental quantities are quantities of A, quantities of B, quantities of C, quantities of D, quantities of E, blah 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 to Z, then those of fundamental quantities will now be either addition, are you with me, or division of these fundamentals. So from these fundamentals, we are actually going to now get our derived, in which maybe we are having two fundamental quantities of A and B. Then here maybe we are having something like a combination, a multiplication of them, giving rise to our A, you know, B. So can you see that our AB is a derived quantity, and they are gotten from A and B, in which A is fundamental quantity 1 and B is fundamental quantity 2. Alright, leading us to our A what of B. Are you with me? So that's the concept behind dimension. So if we are trying to like relate the, what's it called, we are trying to relate if you are trying to relate what, you know, the derived quantities from fundamental quantities, we are actually talking about, you know, dimensional analysis. Like if we are showing the relationship between these two quantities. Are you with me? Quickly, let's look at how we are actually going to, let's look at field theory. So now, if you are actually trying to write the what's it called, the form dimension of any given quantity, you know, any given quantity, be it fundamental or derived, there are key things you need to know. Key things. The very first thing is that you write out your formula. Then number two, you assign dimension to them. Then the third one is you evaluate, or let's call it simplify. Yeah. And you should not forget, you know, our basic quantities, which I give medical laboratory technology. Are you with me? That's your MLT. You should never forget this, because this is what we'll be working with, yeah, the most. We're working with them the most, and as we progress, I will show you more. Are you with me? So anywhere you see mass, you quickly represent it with what? M. Are you with me? Then anywhere you see length or distance, okay, yes, anywhere you see distance, you would represent it with what? Length. And anywhere you are seeing Okay, maybe something like time or something, just represent it with what? Your T, capital T. Are you with me? So these are the three basic things you need to know for now. Let's journey. Let's journey. Let's look at questions. How to look for the dimension of quantities. Yeah, let's go. So now let's check for speed. Let's look for the dimension of what? Of speed. You can tell me the formula, because I told you that for anything you want to look for, you need to know the formula first. Then after that, you assign numbers. Okay, let's call it dimension for it. Then the third, then you simplify. All right, let's now look at it. What's your formula for speed? Very simple now. You know that your speed is the rate of change of what? Of distance with time. Are you with me? Distance with time. So yeah, let's write it. Our speed is the rate of change of our distance with time. Are you with me? Our distance with time. And I told you that our length is actually giving us, like anywhere you say distance, you will replace it with what? With length. Anywhere you say distance, you have to replace it with what? Please don't forget length. Length. Are you with me? That means you are having your L over T. Are you with me? Your L over T. Now let's now simplify. We have successfully assigned their dimension to them. Now let's simplify. How are you going to simplify this? I believe you guys actually you know your mathematics now, your simple mathematics under law of indices and all of that. Mean that this LT now, if T is actually going to come here, if your T would go up, it will now become your LT. Then your T, if T is going up, if T is going up, it will now become -1. Don't forget. So if it's going up, just this one is just coming up now, so it will become -1. Are you with me? So that's that for speed. That's that for speed. Let's do for that of velocity. 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 What is velocity? Don't forget where we are coming from. That we have to look for the formula first, then we look for the dimension, then we simplify as a third distance. So velocity is the rate of change of what? Displacement, not distance. Oh, this one is displacement. What? With time. Are you with me? With time. Meaning that your displacement too is somewhat similar to distance. It's just that the displacement is actually having direction. So this is the difference between your displacement and your distance. So now your displacement also will be given as L. Something like distance, that they are somewhat related. So meaning that your distance will be represented with the letter L. So your displacement will be the same thing, represented by your letter L. So yeah, now let's now continue. So meaning that you're having your L, the one you assign for time, that's your capital T. And I told you that if T is actually going to come up here to become T minus 1, that's LT minus 1. So like T coming up will become -1. So that's the simple this thing. Yeah. So as you can see, speed and velocity is actually having the same dimension. Yeah, they're having the same dimension because they are kind of similar. Because look at their definition too. Rate of change of distance, letter D, with time. But that of speed would be distance, but that of velocity would be displacement. Why this displacement is actually having direction, but this distance is not having direction. That's the difference between the two. Are you with me? So let's go to another one, which is our acceleration. our acceleration. So the very first thing is your formula. What's the formula for acceleration? Acceleration is the rate of change of what? Velocity with your what? With your time. Are you with me? So now, here we are looking at the formula. Looking at the formula now, you should know that we are going to simplify it further. Are you with me? You're having velocity. Alright, you're having velocity, you're having what? Time. And you know that we cannot just assign anything anyhow to velocity. You have to break down that velocity. Again, meaning that you know that your velocity is the rate of change of displacement now. Displacement with time. So we are actually going to add it. So our velocity over time. So velocity is what? Rate of change of displacement with time. Bracket is very rare, so you can, so that you will not be confused. Then divided by your normal time, normal time. Yeah. So now your distance. I told you earlier that anywhere you see your distance, you actually represent it with L from here. Now I told you now. Anywhere you see your distance, you actually represent it with what? L. So now that's that. Here, let's go back here. That means your D here will become L, your time will become capital T. Are you with me? Then your T here also will come capital T again. Now let's simplify. How are you actually going to simplify? If 2T is actually going up, what will it become? To become what? Minus 2. Are you with me? Minus 2. That means our L, our 2T will actually like go up and meet L. So L T minus 2. You know that under velocity here, it was only one here, only one T, meaning that our T will come up becoming minus 1. But under acceleration, 2T is actually coming up. That's why we have it as LT minus 2. Are you with me? So let's do for another quantity. Let's check for the quantity of force. Let's check for our force. All right, force. What is the formula of force? That's the very first thing you have to look at. Force. What is the formula for force now? Your force is given as ma. That's your mass multiplied by acceleration. So all these things are simple. Your mass multiplied by your acceleration. Are you with me? So we're actually going to solve for that, because as you can see, m here will be given as your capital M, but your acceleration here we can't give it anything, because we have to still simplify so that we can actually get our L and T, or if possible the M again. But so now let's continue. The formula: mass multiplied by, what's your acceleration? Acceleration is the rate of change of velocity with time, right? So that means here our velocity over what? Over time. All right. So here we will now do it. Would continue. Can we assign our dimension yet? No, we can't, because velocity here should be simplified again. Are you with me? And we have our formula for velocity as displacement over time. So displacement over time would have to replace this velocity here, because that's the formula now. So we have our mass multiplied by your formula for velocity is what? Displacement over time, then over your time that they gave you before. Then we now begin to write our distance. So here your mass would come down, then multiply by your D. I told you D is always given as L. The dimension of D is L. Are you with me? L. So your L your L. Then if 2t is coming up, I told you to be t minus 2. T minus 2. T minus 2. So yeah, do you get what I'm trying to say? Let me write this very well. I think this thing is not a writing. So okay, now that's multiplied by LT raised power minus 2, right? So, and where is this minus 2 coming from? I told you this is time 1, this is time 2. If time 1 and time 2 want to come together, that means it will be raised power what? 1, 2, that's minus 2. They want to go and meet your L, so that's LT minus 2. So this thing is very simple. You just have to be, you have to be very careful. Yeah, you have to be very, very careful. Are you with me? So yeah, let's go to another uh another yeah question. Let's solve for that of work done. Yeah, work done. You see your work done. Your work done. Let's do it here. Your what? Your work done. So what is work done? Work done is the product of what? Of force and distance. Just like I said that if you want to look for the dimension of a given quantity, you have to know, like you have to note the formula first. So and this is the formula of work done. Let's now solve further. Now what first times, let's use our D, so that let's use our first times distance. Let us use S. Let's use our D. So yeah, what is force? Force is the product of mass and acceleration. That's from your F equals to ma now. Then multiply by D. Are you with me? Then your mass. So we are actually going to be solving further. Then what is acceleration too? Acceleration will be velocity divided by what's time, the rate of change of velocity with time, then multiply by, I told you that your D under dimension and quantity is given as, the dimension of D is what? L. Please don't forget, your D will always be represented by L. Don't forget. So now your M multiply by, let's solve further till we are not able to solve it again. Velocity is the rate of change of displacement with time. Are you with me? Then don't forget to divide it by your time, then multiply by your L. Are you guys getting this thing? We are coming from the formula force multiplied by distance. Then we have to solve further. Our F is ma, that's m multiplied by a multiplied by distance. Then we are solving further again. That's your m multiplied by your rate of change of velocity with time, which is your acceleration, and multiplied by the dimension of d, that's L. So here we now have our m multiplied by, we have velocity over time here, and your velocity is distance, your displacement over time, sorry, then divided by what? Your time, then multiplied by this. So very simple. Yeah, let's continue. So let's now begin to write our dimension. I think they are complete now that we have mass, you have multiplied by your L here. Are you with me? D is given as L now, so your L, when 2t is coming up, what did I say would happen? That would be t raised power what? Minus 2, then multiplied by your L, multiplied by your L. Then your normal mathematics, your normal indices, that means your M. So you have similar this thing here. What will happen? That means your L will become 2. That's from your what? 1 plus what? 1. So we don't need to add it sharp. That's 1 plus 1. Then just write your t minus 2. Then you have your m. L1 plus 1 is what? 2. T minus 2. Very what? Very easy. So yeah. Let's do for another one, sha. Let's solve as many as possible, as many that you can actually meet in your exams. Alright, so yeah, without for let's do for this thing this time around, energy. Yeah, let's do for energy. So now I told you that if you want to look for the dimension of a particular quantity, what will you do? You would actually do what? You'd solve for the formula. Sorry, yeah, I almost got distracted now. So formula. What's the formula of energy? What's the formula of energy? Energy. So energy is just, you don't need to crack your brain. You know, energy is the ability to do work now. Do energy have formula? Yes, it has. It has a formula, and that's your work done. So your energy is also known as your work done. So don't forget your work done. And what's the formula for your work done? That is your force times multiplied by the distance. So that's your energy. That's your energy. So let's now look for the dimension of this particular quantity. So here, let's solve. Your force is given as what? Your mass. So F equals to ma now. So then your d, I told you d, the dimension of d would always be what? L. Just put your L down. So this one we have solved for that one already, like that. So now we can still solve this one for that velocity over time now. That's the rate of change of velocity with time now. So alright, so mass multiplied by my acceleration is the rate of change of velocity, which was with time, multiplied by my L. So let's just move further again. So you see, we can still resolve this velocity again. No? As you can see, displacement over time again. So that would be mass multiplied by your velocity, which is displacement over time. Are you with me? Then don't forget the over time that is under before, so you're not going to make mistake. Multiply by your L that is here. Are you with me? So now so yeah, I think this is our final, where we would actually get our our dimension. Are you with me? So here now, let's try to get our dimension. So our m, all right, then I told you our d is always given as L. D is always given as L, like the dimension of d is L. Are you see? So your L, it's like that, that's your L. Then I told you this T and T, if these two T would go and meet L, if these two T will come up and meet L here, it will become T raised power what? 1, 2. That's T, capital T raised power minus what? Minus 2. Then multiplied by your length. So from the law of indices, now you're having the same distance, you use the law that multiplication will follow plus, division will follow minus. So since you're having the same distance, L and L will now become L raised power what? This the power of L now. The power is 1. The power is 1, and the multiplication would be plus. That would be L. We want to make the 2L 1. So making the 2L 1 will be having 1 plus 1, meaning that my m multiplied by L1 plus 1, then T minus 2, then my m L 1 plus 1 is 2, y T raised power minus 2 be the dimension of our energy. Let's check for another quantity. Let's check for another quantity again. Let's check for that of power. What is the formula of power? The formula of power would be that's the product of force times, that's work done over time. Are you with me? Work done over time. And what is the dimension for work done? We just solved for that, so don't let us still waste board again. You should be able to do this by yourself. So your force times distance, right? So yeah, the formula of work done is what? The formula of work done is your force times distance. Are you with me? Then your time is still what's time. Yeah. So all right. Well, I don't think I need to still keep solving, since we've done for work here. So let's just make our work easier. So the dimension for this is that's for your work. Just write it, ml 2t minus 2, then divided by your time. Then you begin to solve. Now, alright, so I'm having my m. I'll write my m down, then my L, alright, that still remains my L, and my L is not competing with other L, so I don't need to resolve. Then my T would compete with T here, so we have to resolve. We're having two T. What are we going to do? According to the law of indices, since they are the same here, we have to resolve for their powers. So making the T, we'll make that T1, then it will now be, that I told you now, under the law of indices, anything that is divided would always go for minus, and the multiplication would go for what? Plus. So since you are dividing here, so the powers will be subtracted. So that's your -2. Then your divide, that's minus, this one is carrying what? 1. So that will be your ML2. So your -2 minus 1 would be T, that would be -3. And that's how we get the dimension for power. Are you with me? Dimension for power. So let's do for, you guys should be able to solve for the others. You guys should do for that of impulse. Are you with me? Do for impulse. Should be able to do for momentum. Should be able to do for your electric field, or let's say electric potential. Should be able to do this. Should know your formulas. Should be able to do for many more, the likes of your tensile stress, your tensile strain. Are you with me? Your tensile strain, your Young modulus. Okay, I think that's actually sounding, some of you will be like, which one is tensile stress, which one is tensile strain. Alright, let's do it. Now, your tensile stress, alright, tensile stress. So tensile stress here is actually, coming from Young modulus. You know that your Young modulus is the ratio of comprehensive or tensile stress to comprehensive or tensile strain. Now, what's the formula for tensile stress? Tensile stress is actually having that same formula with pressure. That's force over area, the force per unit cross-sectional area. So we see that this tensile stress is having the same formula as pressure, so you don't need to cram. When you see your pressure, you actually see your tensile stress, and because of this, the both of them would have the same dimension. Are you with me? Are you getting the logic? Now, our force over area here, so we can simply look for the dimension, and that would be the dimension of tensile stress. Now let's check. What's the formula for force? Our force is mass multiplied by acceleration. Are you with me? Then this one is simply your area, and your area is your length multiplied by breadth. Are you with me? So we now have, let's continue to resolve this, because you see that our M is in its dimension already, but our A is not in its dimension. This acceleration is the rate of change of what? Velocity with time, right? So meaning that I'll continue, so mass multiplied by my acceleration is the rate of change of velocity with time, coming back to my length. Dimension of length remains length. Dimension of breadth is length. Are you with me? Are you getting the scope? The dimension of breadth cannot be breadth. The dimension of breadth will be length. Don't forget. And don't forget that I said that the dimension of distance would always be what? Length. Please don't forget that also. So I think we are good now. Let's continue solving. Is it hard? It's not hard. It's very simple. So here, so we are still solving for tensile stress, right? So our tensile stress dimension, so we'll have let's continue, our mass multiplied by, we have velocity over time, right? Then we can still resolve this, we can still continue solving this, making us, okay, like velocity is what? Rate of change of displacement with time, right? That means it will come here. Rate of change of displacement with time, that's for velocity, then over our time again, over our normal time. Are you with me? Then divided by your L multiplied by L, your L square. Are you with me? Are you with me? So now, yeah, let's continue resolving. We have our M multiplied by this. I told you your D is represented by L under dimension. Then if this 2t is actually going to come and meet the L, what will it become? That's 1, 2, that's raised power minus 2. Are you with me? Then divided by your L2. Now, using the law of indices, we have our M. Let's make the 2L 1. So that means the powers will suffer for it. This one is 1 and be 1. Divide will be minus now. Minus the 2. So we have successfully made the L1. Then our T raised power what? Minus 2. So and that's, we're able to get our dimension. Let's solve further. Then ML, then 1 minus 2 will be minus 1. Then T was minus 2. And then you get the dimension for stress. And please take note, this dimension for stress is also the same for that of your prayer, because they are having the same what formula. They are having the same formula. They are having the same formula. Are you with me? All right. So that's about tensile stress. So when you see tensile stress, don't look at it and say which one is this. You solve very fast and tell them that does it mean that you are giving simple stuffs. All right, so you should be able to do for tensile strain now. So you have done for that of tensile stress. Let's do for tensile strain. So yeah, let's do for strain. Let's do for strain. Tensile strain. All right. So what's the formula for strain? Formula for strain is, your E over L, that's small e over L, that's your extension divided by what? Your length. So that this is your formula, and then they are both measured in what? Either millimeter, meter or centimeter. So both units will cancel, so they are unitless. They do not have units. Tensile strain do not have what? Units. Can you see the units cancel each other? And as well, they are dimensionless. Because as you can see, both of them are lengths. Length would cause extension, and extension would cause length. So both of them are lengths, and that's why they are measured in the same unit. So tensile strain has what? No units. Are you with me? It has no unit. So let's do for Young modulus. Know that our Young modulus is actually given as tensile stress divided by tensile strain. Are you with me? So that means the ratio of tensile stress or comprehensive stress to your tensile or comprehensive strain. You are talking about what? Young modulus. Now let's try to find the dimension of Young modulus. Now what I told you now, under looking for, when you are looking for dimension of a particular quantity, there are 3 key things you need to know. Don't forget, you have to check for the formula first. So and we've done that. Then from there you resolve, give them dimension, then you simplify. Are you with me? So let's check. What's the formula for tensile stress? The formula for tensile stress is what? Your force over area. Then we have for that of tensile strain as extension over length. Are you with me? And then the tensile stress. Okay, let's write it out again. We have our force over area. Are you with me? Then divided by your extension over your length. Are you with me? Then by your length, then we have yeah, let's continue. So this is a formula for Young modulus. Are you with me? Young modulus. Yeah, here we would have our force, which is what? Mass multiplied by acceleration. Then you have your area, which is your length multiplied by breadth. So that's for the tensile stress. Then your E over L, still length, yeah, your length too. Length. So both of them is having the same dimension. So they will cut themselves out. They're having the same dimension, they're having the same units. So they will cut each other. So they are dimensionless. You get, so 0. Are you with me? So now we are left with MA and length over breadth. So length times breadth, sorry. So yeah, we would continue. Are you with me? So our mass, we are left with mass multiplied by acceleration, then divided by length times breadth. Your breadth is given as L now, expressed as L from what we've been discussing. So mass multiplied by acceleration is what? Velocity over time. All right, then yeah, continue. Length multiplied by length, then we have it as mass multiplied by v can be further resolved to rate of change of displacement with time, pam, then divided by, don't forget your time please, you had. Are you with me? We've done this before, I'm still doing it again. Then divided by your L of L. Are you with me? Then you have your M. Are you with me? Then multiplied by, if these two t come and meet this our L of something, so 1 2 abi, that's raised power minus 2, then divided by your L multiplied by L. All right, that's your L square. L multiplied by L square. So your ML, so we're having L up, we're having another L down here. So if the two will become 1, we obey the law of indices. So their powers now be, this one is carrying 1 now. So the division sign here is telling us that it will be a minus. Then minus 2, t minus 2. Are you with me? So then your 1 minus 2 will be minus 1. Are you with me? T minus 2. And that would be the formula of your what? Young modulus. You with me? So all right. So your assignment, you should solve for yeah, what is it called? Yeah, solve for gravitational gravitational constants. So solve for your heat energy, find their dimension, solve for surface tension. They are very simple. Solve for them. These are things you need to know. Your electric potential. I'm not solve as many, as many examples. As many as you can. So it will help you. It will help you reinforce what you've learned. Are you with me? So yeah. Now we have dimensionless quantities. Dimensionless quantities are those quantities that they don't have units. They don't have dimension, and as well they don't have units. So they are dimensionless. They don't have. An example of these things are your force ratio. You will check force ratio. Force ratio did not have dimension, because the formula says output force over input force. Are you with me? So it does not have dimension. We have our mechanical advantage. Mech advantage, that's mechanical advantage, is given as load over effort. Both are forces. So this one will be measured in Newton, this one will be measured in Newton also. in which the Newton will cancel Newton out. So they have no dimension. They have no dimension. We have that of velocity ratio also. Yeah, we have quite numbers of examples. The velocity ratio. This one is, the formula says distance moved by load over distance moved by effort. So this one will be measured in meter, this one 2 in meter, this one will cancel this one out, meaning that it has no units, it has no dimension. So we have that of our coefficients, our coefficient of friction, our coefficient of what? Of coefficient of friction, so and many more. So these are quantities that are what? Dimensionless. Alright, it's your surgical medic and is rooting for you.